right, good morning, everybody. My name is Rebecca Vieyra, and my husband and I are co-presenting.
Yes, I'm Chrystian Vieyra.
And so you've come here to basically learn a little bit more about ARCore, and what we'd like to do is to share with you a project that we're working on that we think will also kind of give a good general overview of ARCore, some of the opportunities, also some of the caveats associated with it. I do want to let you know from the very outset, though, the kind of expertise I bring to this partnership is one which is really about physics and also about education. So I'm a prior high school physics teacher who now works in international diplomacy in Washington, D.C., and so it's kind of an interesting combination, but my role here is really to help make linkages.
Yes, I'm Chrystian Vieyra. I'm a software developer. I do mostly mobile development in Washington, D.C.
And so we work together, and what I've got here is an image of some colleagues of mine. I now predominantly work with teachers in an international context, but I want to take us back just a couple of years. When I was teaching high school physics, it was kind of a rite of passage to take students like to an amusement park or to Six Flags in order to experience physics in the real world. Has anybody do that? I'm just curious. Okay, so you know what I'm talking about, right? And so I had this kind of very narrow vision for how I wanted my students to interact with smartphones. I knew that there was an opportunity to use to develop apps, and there weren't very many apps at the time that were doing things like displaying and visualizing accelerometer data. So I asked my husband to develop that, and ultimately, within the span of just a couple of years, we went from only my students downloading the app to having more than 2 million users all around the world, every place where Google Play was available. And we added to it not just things like accelerometer, barometer, but we started adding as many sensors as possible and started finding that not only were university faculty and researchers using it, but people who are involved in acoustical engineering, people involved in the medical field, et cetera.
Yes, so Rebecca came to me and asked me to develop these apps for her students, and I started realizing all the sensors our phone has. You know, you have seen the accelerometer when you rotate your phone, portrait and landscape, that's the accelerometer. We also have the gyroscope to detect rotations. A bit more uncommon one is the barometer, where you can measure the barometric pressure, and that's usually used in conjunction with your GPS module to get a faster lock on your altitude. And the microphone, which measures sound intensity, and a special one I particularly like is light intensity. We can measure how bright the room is with the sensor in your phone. And you see that with the automatic brightness adjustment of Android. We created a website on our company, Physics Toolbox. We have free apps for students, high school, college, any level, to collect and visualize sensor data within their smartphone.
So again, as I mentioned, what we're going to do is to take you through this kind of story of development and share with you how we worked with ARCore. So we're going to point out some of the opportunities. And again, I look at this very much from an educational standpoint, not only as a classroom teacher, but as an adult learner as well. So how do we people learn to have visuospatial awareness? How do we help people to understand the concept of fields? It's just kind of like a starting point for the way that we can think about using AR. And of course, we'll also share with you some of the specific challenges unique to ARCore. So some of the things we're going to talk about will be general. Some will be specific to magnetic fields, but it's not just about magnetic fields. I want to make that clear. So if you're interested, you can download the app. It's called Physics Toolbox AR. That's our standalone app. We do also have Physics Toolbox Sensor Suite, which has the AR as a mode embedded within it. Now, the reality is that depending upon your kind of device, you may or may not be able to run ARCore, and that's part of one of the things we're going to tell you about. If at any point you would like to play around with it, our daughter Therese is in the back. She's got some magnets she can pass around. You're welcome to do that now or after the presentation as well, and we're happy to help you out with that. So the project that we're currently working on deals with visualizing magnetic fields. It's been funded thanks to a pretty large grant from the National Science Foundation. And our goal, again, is to visualize magnetic fields, but really it's an excuse and an opportunity to try to push the technology. We work with a physics education researcher, a cognitive psychologist, and also with an astrophysicist who understands the value of needing to visualize the invisible. So we'll go ahead with just a very brief overview of...
Yes, so AR. AR stands for augmented reality, and that is the illusion of having virtual objects in the real world. I think the greatest example of this is Pokemon Go. Couple of 3-4 summers ago, it came out, became super popular. We were looking at our camera viewfinder and seeing the 3D content, the Pokemon and the Pokeballs overlay there. Another great example of that is IKEA. You can download the IKEA AR app and see how the furniture looks in the 3D assets from their furniture and how they look in your living room and house. And as we looked at the opportunities and the app frameworks that we could use for AR, we decided to settle on ARCore for our Android app to visualize the magnetic fields.
So I briefly want to provide some context as to why we're interested in physics, and because that's going to kind of help color the story a little bit. And so the first thing I want to ask, how many of you have ever had the opportunity to shake like iron filings over a magnet? Hopefully. Okay, awesome. That's great. So if you've done that, you've probably gotten a very two-dimensional version of seeing magnetic fields. And what we're trying to do is we're trying to make that representation more robust. It's important because magnetic fields pervade our entire existence here on planet Earth. As you might know, it protects us from all those solar rays, which can be quite damaging, that come from the sun. Sometimes you'll see it, well, actually, one thing that's, I think, really cool about this that people are a little bit surprised by is that the magnetic field doesn't typically point flat. When we think about compasses, we think about magnetic fields, kind of pointing towards the North Pole, so to speak. And if we had a truly flat Earth, that would kind of be true, but we don't. We don't live on a flat Earth, and the fields are not curved. They're quite loopy. This image was taken by one of our advisors, Anne-Marie Pendrill, near Stockholm, Sweden. Here's a picture of the Earth's magnetic field, the vector showing the field, showing the magnetic intensity and direction while I was in Lima, Peru, so near the equator. And then again, another image from our colleague down in Australia, where the magnetic field points upward. That may not be a big deal to you, but as a physics educator, it's very important for me to help people challenge their ideas, to become critical thinkers. And so that's what this app, one of the things that we're trying to do with this app. You've also seen evidence of magnetic fields and their interaction, probably, with particles, electric particles, things coming from the sun, and maybe even if you're driving down the highway, you may have also seen this as well. I don't know how evidence-based that is, but there seems to be some interesting tendencies. So what we're interested in is how we can visualize these things using AR specifically. And this task is really quite different from most everything else that AR is trying to do out there currently, because we have 3 challenges. The first challenge is just to get ARCore to do what it's supposed to do, which is to understand where the phone is or where the device is with respect to where it started and with respect to the environment. That's kind of the standard challenge for everybody. The second challenge is to link that data up with sensor data from the magnetometer. I haven't really seen that done in any other AR apps, but I would love to be corrected if I'm wrong. And then the third challenge is to display that data, in this case, the field vectors, in a way that conceptually makes sense to the people who are looking at it. Those are not small challenges. This is basically our final product. We've still got some UI things we need to do. But basically, I'm going around a stack of magnets, which is kind of like a bar magnet, and you'll see the field vectors, and you'll notice a couple of things. It looks a little bit like what you saw with the flat magnet, except there's a 3-dimensionality to it. And if I wanted to, I could go over the magnet multiple times and get multiple layers, or if this was on a table, I could even go under the table and get multiple layers of information there too, and then I can move through that field. So This is kind of unique. We've got floating vectors. We've got vectors that have these different rotations also, and that are also reflecting the strength of the magnetic field as well. So with regards to measuring, we have to really understand how ARCore works. How does it know where it is and what it's doing? And Google's got this very kind of nice breakdown that says motion tracking, environmental understanding, and light estimation is how AR basically works in terms of just understanding where it is and how to generally try to display things. When it comes to motion, there's two senses that your phone really, really uses. The first one is visual odometry, so basically it's sense of sight, and the other one's inertial, which is kind of its gut feeling. And so, many of you probably have again done this, where you put your finger out, close one eye, look at your finger, and then close the other eye, look at your finger, and you might notice that your thumb, that your finger, whatever you're holding up, appears to shift with respect to the background. So we typically use two eyes, and that vision combines, and we get a sense of parallax. We can tell depth. Not all animals, and your phone also, does not have that capability. So do any of you have a hamster at home? Anybody? One person. This is sad. Hamsters are the best little animals. We've had one, I think, almost every year since our daughter was born. So we love hamsters, and one thing you note about them, they often stand up, and they look side to side. Also, if you've got rats near your house, you'll see the same behavior, right? And part of the reason why they do that is they have got independent eyes. And what they're doing is not just looking around, they're often trying to get a sense of parallax, to get a sense of depth perception that otherwise they won't have. So your phone, when you start ARCore, will often ask you to move or to wiggle it around so it can get a sense of depth perception based just on vision. The second thing that your phone has is a sense of gut instinct. When you're on a roller coaster, you feel it in your gut, you feel it in your stomach, and your ears also give you some sense of whether or not you're accelerating up or down. This can be sensed mechanically. So here I've got some high school students who are inside of an elevator with a spring, with a computer attached to a force plate, a standard scale, and also a phone which has an accelerometer inside of it. And it can tell when you're accelerating up or down. Yeah. And sometimes these can be dissonant.
Yes, so I had some sensory dissonance a few months ago. I live in Washington, D.C. I was taking a very long train to Boston. Here I'm showing a video in the metro, but anyway. As I was traveling, I was deciding to test the app, and as I was placing the vectors, the arrows, they kept, I'll replay it again. I would place them and they would go away. They kept going away. It took me some time to realize that ARCore was not only looking at the environment with the camera, but it was also using the accelerometer to sense that I was in motion. So the arrows were actually staying where I put them. I moved. And a good example of the opposite is I'm on a plane and my frame of reference is not changing. It's not accelerating, so I'm placing the vectors and they're not moving.
And for those of you who might have a little bit of electronics background, microelectromechanical systems really are what are inside of your cell phone. This is a kind of multi-plated parallel plate capacitor, and so you've got kind of a grid that's able to vibrate, or able to basically move with respect to how the phone is moving. And in doing so, there's another grid which stays stationary, and as the distance between the parallel plates shifts, you get a change in capacitance, and that's interpreted as acceleration. So the point here is we're able to take all of these sensors and we're able to connect them to one another. And when all of these sensors combine together, you're able to do some pretty awesome things that you weren't able to do before. This is just another video of one of our prototypes, and something that I think is kind of interesting. You'll notice there's an offset from the actual magnet. That has to do with the fact that the camera, even though the camera is somewhere up here next to the magnetometer, the camera image is displaced to the center of the phone, if that makes sense. And so this is kind of a challenge we're trying to work through because phones are so different that's something we're probably going to try to have people do manually. So measuring and understanding how AR works is critical, but now we had to link that data, link that AR spatial understanding to the magnetic field sensor. And so the question is, how do we do that? And that took a little while. Yes, so
the phone has a magnetometer, which is a tiny MEMS sensor placed in your phone, usually in the top part of your phone near the camera, one of the sides of the camera. And Android has been having an API for this since level 3, so since almost the very, very beginning. And you can get the sensor values for any sensor, and in particular here the magnetic field sensor, calling a sensor event. You get a sensor event every time it happens. It's the type of variable is a type magnetic field. And here's the function. I get as a result of this function 3 values. The sensor gives you 3 values of the magnetic field in the X field, the magnetic field in the Y field, Y, X, and C coordinate system. And I get those values. And now that I have measured that data, I can calculate the inclination and the declination of the magnetic field vector.
All right. So once we've linked to that, then our challenge was to display. And this was actually probably the hardest part for us because we ran into a lot of obstacles that we've actually heard from developers in the past couple of days. They've also encountered when it's come to displaying this kind of stuff. So I'm going to let Chrystian walk us through that.
Yes, so ARCore is essentially defined by 3 parts. Motion, which Rebecca already explained, and environmental understanding. And environmental understanding has 3 major points. Feature points. ARCore is looking at the environment with the camera, with the hamster vision around to see if it can find relevant features in the scene. So here you can see the hand when you launch an ARCore app. Unless you disable it, you see this little animation that is asking you to move the phone from side to side. That's for ARCore to get some visual odometry of the environment and see when things are relevant. And feature points are just important features that ARCore finds in the scene. Like here, I'm pointing it at my keyboard, and it's finding the edges of the keys as relevant points. It knows that there's something special about them, the pixel change. And once you have many of those features, ARCore can define that there's a plane in it, a horizontal plane like a table or the floor, or a vertical plane like a wall. And ARCore already provides for us developers 3 types of plane detection. So you can detect planes, horizontal planes, verticals like a wall, and horizontal and vertical planes. And here's an example directly from Google, one of their ARCore samples on GitHub, how I'm pointing the camera at the floor, and it's detecting the plane, and I'm adding the Android figure in it, vertical and horizontal planes. And to do that, we use something called hit testing. So our phone has a 2D screen. So when we tap on the screen, we're selecting a point in space. And once we already found a plane on the ground, ARCore detected a plane on the ground, we can tap on the phone, and ARCore will do some calculations to try to see a point where you tap, cast like an imaginary ray of light to that point in the floor, and see if there is a match. If there is a match between where you tapped and the floor, it means that there's a plane, and you can place objects like the little robot I put before.
So I'm going to show you one more thing. This is the Earth's magnetic field. So this is, I don't have a permanent magnet, but what you'll notice is these are, again, all floating. So we can't use something like hit tests to help us. We can't anchor things. We can't anchor these vectors quite as easily as we could, like placing a digital or virtual cat onto a table, for example. And that will introduce some additional problems we'll come to in a moment.
Yeah, and the last part of ARCore is light estimation. And this part, it hasn't particularly been very relevant or easy for us to understand in our project, but basically ARCore can analyze the image feed, each frame, and can find where the light source is. And once it finds the source of the light, it can cast realistic shadows and reflections in your object. And here I have a demo of the scene form in GitHub, and you can see how the main source of the light is to the left, and the sun and the planets are casting a realistic shadow on the right side.
And this might feel like bells and whistles, but one of the things that we certainly know from education research is things like shadows are extremely critical in terms of helping people to have a sense of perspective. And again, going back to those visuospatial skills, which is not exclusive to astronomy or exclusive to physics, but is incredibly important for any kind of three-dimensional modeling. So that's something we're definitely going to be testing in our education research work.
Yeah, and so we just talked about ARCore. Now we need to talk about how do we actually visualize these things. ARCore finds and understands the scene, but we need a way to place objects in the scene. And you can always use OpenGL, But in my case, I decided SceneForm is the best way to place objects. So SceneForm is a framework from Google that takes care of the rendering. It uses the filament rendering engine, and you can render objects in 3D. And SceneForm as a library is a bit underdeveloped, I think, compared to alternatives in different mobile platforms. So for instance, the only three types of shapes that you can create built in on SceneForm are a cube, a cylinder, and a sphere. So as I started developing this tryout, I started playing out with spheres, placing them around magnets as I detect the field, and I trying to change the intensity of the color. And as you can see, the closer I'm to the magnet, the redder the spheres are. And spheres, it's just a factory pattern to place the objects, call them, and the units used to place how far away from the camera, the object, the phone, to place the objects use the metric system, not the imperial, which I really like, because I'm from Mexico and we use the metric system. And as I'm not a designer, I tried to find for resources, where can I find a good arrow for my app? So Google Poly is a great website. I think of it like the GitHub for designers. They place their 3D designs, 3D assets that you can freely use in your app as long as you cite their work according to their license. And or IDE, Android Studio, has a wonderful plugin to visualize these objects. So you can see the code of your 3D asset you imported, and you can see it render within your IDE, so you don't need to launch the emulator or your device. And the same engine that is used to render the in your IDE is exactly the same as in your phone. So the objects will look exactly the same render. And here I created a simple function to load the asset, which is the arrow I found on Google Poly, and I'm placing them in my project, and I can just call it every time that I tap on the screen.
So when it comes to actually placing these vectors, which can be in any orientation, this is one of the biggest blockades that we kind of ran into. I think it actually took a few months for us to figure out exactly what we were doing wrong, because I thought, come on, this is silly, stupid. I mean, I thought it was super simple. Long story short, when it comes to placing a vector, right, the vector can be any angle, but your phone can also be any angle, but it also needs to know where it is, and and how it's placed, what that angle is with respect to the ground. So it's kind of like the universal gyro bowl kind of problem. If you have had a little kid, they might tip over bowls and things, and so this is supposedly a solution product where it's basically got 3 different kind of axes. You can turn it. You can even flip it upside down, and the cereal or whatever you've got in there will not spill out. So we have to represent multiple different kinds of frames of reference and respective rotations when we're dealing with what we're trying to work on. And I thought it was super easy. I thought, well, we just use simple Euler angles, like middle school geometry class. But that presents a problem. To give you a visual of what I mean by the problem, so this is called the MAT. I went to space camp last December with my daughter. And the idea here, this is the thing so that if you end up in a barrel roll, you can try to figure out how to get out of it in space. But basically, as I rotate through, there are times when the gimbals, when these rings might line up, 2 or more of them line up at once, which prevents you from rotating along particular angles. There's a limit at which you can't actually rotate in a direction that you might want to rotate. Mathematically, we run into the same problem. So right here, so basically I've got, I think, 3 moving gimbals. If I really wanted to avoid problems, I need to have a 4th gimbal, so I never, if I lose a degree of freedom, I still have 3 degrees left. This problem shows up in this right here. We've got an arrow, which is unfortunately a 2-dimensional arrow, but you can tell it's kind of anchored to the ground or anchored to the front. But as we entirely rotate the phone, it experiences a very kind of bizarre behavior. You get this strange flipping. And if you actually get yourself a gyroscope and try moving around with it, driving it with a car or something like, there's some awesome YouTube videos where you can actually see how you get this awful flipping that happens when it approaches gimbal lock. And so mathematically, we have to deal with that. back in the day, this is Apollo 11, or at least that's supposed to be a picture of Apollo 11. One of the astronauts, Colin, he was trying to reorient himself, and every time he oriented himself and came very close to a gimbal lock, he would get super angry because he had to reset it according to the background stars. And so there's a really awesome transcript you can listen to where he tells Houston, for Christmas, I'd like a 4th gimbal. And the way that we deal with these problems nowadays with these inertial units and helping to visualize and understand 3-dimensional rotations is to use something called quaternions, which is a type of mathematical representation where you kind of project onto a 3-dimensional representation a 4-dimensional world. And if you're curious to know conceptually more about it, there's some fabulous YouTube videos by 3 Blue 1 Brown that explain it really well. And it wasn't until we understood this that we were able to visualize our field vectors.
Yeah, and this honestly took us an incredibly long time. I am not a game designer, so I just think in 3 dimensions, X, Y, Z. So thinking that I had to add a 4th unit vector to my components was beyond me. So if you're a game designer, this makes sense because you're dealing with object rotations. I'm not a game designer, so I struggle with that. And even back in the 1800s, William Hamilton came up with the idea of quaternions, this complex visualization of math. And if you're familiar with Lewis Carroll, he wrote the book of Alice in Wonderland. He was a mathematician. Lewis Carroll used a pseudonym for that. And there's a scene in Alice in Wonderland where there's 4 characters, 4 components of your vector quaternion: the Alice, the Mad Hatter, a hare, and I forgot the 4th. But anyway, there's 4 people, and they are endlessly walking around a table, which is just one plane. They're endlessly shifting and walking around. And Lewis Carroll was mocking the idea of quaternions and quaternion multiplication because it's so beyond us, normal people, to see. It's so confusing.
And apparently, Chrystian told me this morning, quaternions were developed before an application was necessary, so people didn't understand the utility of it. So it's just very nice to participate in that process of discovery, and we hope that you can participate in it too. All right, so in brief, before we close, we do want to make sure that we share with you some of the caveats of working with Google ARCore.
Yes, so you need an Android device with a Google that is compatible with Android 7.0 or newer. However, you also need to install an app provided by Google called Google Play Services, AR. So your user has to go and install your app and also install an app, Google Play Services for AR. And device compatibility is a bit sketchy. Not all devices are compatible. Your device, in general, needs an accelerometer, a gyroscope, and to be whitelisted by Google to install their own app. Device compatibility gets complicated. Some devices are compatible with Android 7.0. Some require Android 8.0. And in some Xperia devices, you not only require Android 8.0, but you require Android 8.0 and a certain security patch level, which further, I think, complicates the idea for the user to know if their device is compatible or not. And case example of delayed AR support. Not all devices that are compatible with AR are released with compatibility. Last year, I purchased a Rebecca Galaxy S9 in March 2018, day 1. And then ARCore was not compatible with the Galaxy S9 until May 2018. Almost 2 months and a half of that flagship device not being compatible with ARCore. I also experienced it with my OnePlus 7T Pro. It was like 30 days I couldn't develop AR apps on it because it wasn't compatible according to Google. Another problem I think users have is branding. At first, you had to install the ARCore by Google app. But since August, you have to install the Google Play Services for AR app. So I think it brings some brand confusion. And for our project, if you want to have an AR project, you must target Android 7.0 or newer. However, you can make AR optional in your manifest, and that way you can lower the API requirement. And for our main app, Physics Toolbox Sensor Suite, we decided to integrate the AR as a module into our app, which I think is the best way, because not all devices are compatible with AR. And when your AR parts of your app might be bringing extra size assets, increasing the install time and size into your user's device, and you don't want to install AR parts of the app into a device that is simply not compatible with AR. So you can do a module and install or runtime, install or not the AR components.
So drift, of course, is going to be any problem, pretty much in any kind of a context where you're trying to map motion. And in our case, where we are plotting data and trying to plot it with respect to where it was previously, we're going to have some drift problems. We can avoid a lot of these problems by teaching users how to not move too fast, how to have backgrounds that are stationary, but also have a lot of high visual contrast. But this is just an example of I had a ball that's a little model Earth that I'm using in a context with university faculty. And you can see that the field, which is really quite beautiful, over time will eventually drift. And so one has to be willing to have a little bit of frustration as a user and learn how to move with it properly, basically.
As the experience can be very frustrating, we want to communicate that to the users. So in our app, we have a bunch of helpful messages because ARCore will give you the state of the session. It will let you know if the scene is not too bright, so it cannot find objects, ask your user to move around, and try to make this experience less frustrating to the user. You can give them helpful information.
And let me be clear, it works well when it works well, which happens very frequently when people know how to use it. So on that note, I think the question we ask ourselves is, where do we want to go next with AR? Already our work was really based in education, started with education. 60% of our users are educators, predominantly university faculty, and science and STEM education researchers. But we have a huge crew of people who are doing other things. And why magnetic fields? Why fields in general? I do just want to put a shout out there again to our sponsor, the NSF. There are two things that they really feel are very important. I think they have a list of 10 of these big ideas for the US. And the first one is making sure that we understand the human technology frontiers. How do we help people to interact with technology? So again, this isn't just about magnetic fields. It's also about how do we use devices and how do we think about them as being useful to us. The second thing is harnessing data. How do we help people to visualize and to understand data? So I know we're very far from Washington, D.C. The NSF is like in our back door, and I think they do fabulous work, and they do a really good job of helping me to think about how can we get technology to align with some of our national goals for society, for the economy, security, et cetera. And then in closing, what I'd like to say is a few years ago, I was a high school physics teacher, and I think I was a pretty great physics teacher. But my vision was very narrow. It was very narrow for what I think we can do with sensors, with technology, with mobile devices. What I had in mind was a solution for my students on Physics Day once a year. And what has come out of that from those who are not educators, or not predominantly educators in our user base, has been people who are using things like smartphones and attaching them to people's hands who have limited mobility to find out how they do move, so they can do things like redesigning spoons so people can take care of themselves. We've also found scientists who use things like our light sensors to make kind of these makeshift on-the-field devices, so using using the light meter to basically find out whether there was enzymatic reaction. If you don't have a laboratory nearby or you're in a developing country, this is the kind of stuff that you can use. And then lastly, this is the one that I think I'm most proud of. This recently got published. There's a nurse I believe she's a medical doctor, but she works with the Outback in Australia. And she brings in these very premature babies and flies them on helicopters to hospitals. And they've found that a lot of the things that our phones can sense, like vibration, sound, and light, those things have critical influences on children's survivability during that transportation. And so she's been doing research to find out what do they need to do to minimize those kinds of stressors on children. So none of that is AR. But in combination, when we think about AR, where can we go from here that really helps to improve people's qualities of life? So that's what I'm always asking myself is, where can ARCore take us? And I hope now you might think about, where can ARCore take you? Thank you so much.